Hi everybody, and thank you for joining the Advanced Technology for Programming Complex Assembly Task session, in which we will discuss the ArtiMinds plugin inside Process Simulate. So let's go right ahead and start. I would like to begin with discussing the main challenge, the main modern challenge with the customers when they come to build and implement the robotic system. So the recent International Federation of Robotics insights show that the biggest part of the lifetime cost of an industrial robot comes from the time and effort spent on the application layer. And most of it is the application software. So this cost becomes higher when required changes and adaptation become more frequent. At the same time, the hardware and other operating costs become marginal with less room for saving. It is evident that the process of creating the application software has the biggest potential for cost optimization. It is also evident from the same research that the very significant cost in the application layer is the programming and reprogramming cost. And it probably has the most room and potential for optimization. So if you look at that, what would be the main important improvement factors? So first of all, we would like to be able to reduce the programming and validation cost. It would be great if we had a more straightforward, standardized, easy to use programming method. In order to enable more people and that require less highly skilled experts in order to program the robots. I would also like to minimize the production time losses associated with the programming and reprogramming tasks, which are required to adapt to changes or manufacturing variances on the shop floor. And we would also like to be able to have more flexibility or more range of applications to which we could apply our robots to. And by integrating the latest technologies in the market, like computer vision and force sensing, at the same time being able to plug them in an easy to use and straightforward way as well. So we don't want to spend a lot of effort on integration of various sensing technologies. We would like to be able to do that in a more plug and play fashion, which is much easier and straightforward. So at this point, I would like to introduce our partner company, ArtiMinds Robotics, located in Karlsruhe, Germany. So ArtiMinds developed a software called Robot Programming Suite, which is based on an intuitive approach. As a user, rather than writing the program explicitly in the robot program language, you're actually using templates or skills from a predefined extensive library. And the intelligent software is automatically generating the program in the native robot language, which eliminates the need to write explicit code altogether. So this method makes robot programming much easier, and it is also robot vendor agnostic. You use the same programming method with all robots. Moreover, it allows you to easily program force and vision or adaptive tasks in the same straightforward way, using a library of templates instead of writing the explicit code, which makes the range of applications that you can apply the robot to much wider and more diverse. So what we did here is that together with ArtiMinds, we developed a plugin of their software integrated in Process Simulate, which enables our users to benefit from the extensive advantages of the combined program. So this gives you, in addition to the traditional Process Simulate advantages, a lot of new benefits. So first of all, as I mentioned previously, the ArtiMinds technology of templates-based programming is implemented here the same way. And so you can use the predefined templates, which are designed to common assembly scenarios, and thus you can facilitate the programming task, reducing the need for reinventing the wheel, so to speak, every time, and the need for high-end experts. By using this approach, you can be more flexible, as I mentioned, with the applications that you apply the robot to. So you can use various configuration, you can program various assembly tasks, very diverse, you will see in the next slide. And you also have different programming method flexibilities, which means that you can program either completely offline with the virtual robot. You can program connected directly, interactively to the actual robot. You can combine both methods. You can even work in a hybrid environment, which combines working with the actual robot, but still using the simulation environment to validate various aspects of the process. You gain the robust handling of manufacturing variances, and this is very important. So instead of using hard automation, very precise tolerances, the force-torque sensing adaptive motions, which are implemented inside the templates, allow you to address those variances without introducing those hard automation aspects. So it's very precise equipment, it's very precise fixtures. Basically, the robot itself, which is equipped with high-quality sensing technologies, can compensate for those variances the same way as the human operator would, by being able to use vision sensing and tactile sensing. So as I mentioned, multiple robot brands are supported by this solution. And of course, this established the platform for you to benefit from the reduction of effort and money spent on the programming and the programming tasks. So let's quickly see how this works. So here you see the process simulate environment, and the way it works is as a standard viewer, like any other viewer in process simulate. So you see here the graphic viewer of process simulate. On the left, you have the programming interface of the ArtiMinds plugin, and you basically program by parameterizing predefined templates and create the tasks out of the templates. And the only thing you need to do is basically parameterize the task through a user-guided wizard interface that you have here. So this is the library. It has tens of predefined skills adapted to various scenarios, from simple movement from point to point and up to very sophisticated templates like controlling spiral search, spike search, and other sophisticated patterns that address various challenges of assembly tasks. So when you select the template, you drag it into the programming area and basically create a sequence of templates, one after another, according to what you need. And by using this wizard for this specific task, for example, here, it's a grasping template. It basically guides you through the steps you need to in order to parameterize the task, which means teach some reference points and tell the gripper fingers when to close and when to open. So this allows you to complete the programming task in just a few minutes and quickly validate this in the digital twin and subsequently download the program into in the native robot language into the robot controller. Let's have a look at the demo to illustrate it further. So here we have a robot, Denso in this case, that is required to perform a typically manual task of a PCB component placement. So using the RPS plugin on the left to the graphic viewer, you select the spiral search template from the template library. And the programming wizard guides you will see in a minute after you drag it to the programming area. You see how the programming wizard guides you through the steps required to parameterize the template for the specific assembly task. So once you have parameterized the distance, the reference the starting point of the search, starting points of the search actually, there are several. And then you basically also parameterize the required forces to be applied in order to insert the component. And then you start simulating the result. And in the virtual, first of all, in the virtual robot. And once you validate all the aspects of the program with a virtual robot, you can quickly skip to the actual one interactively and test it also with the actual one, with the physical robot. And then subsequently, once you will be happy with the result, with the physical robot tryout, you would be able to download the robot program to the controller and ready to deploy on the shop floor. So you see here now we switch to the physical robot, which is now inserting the components. And as you can see, there is a very delicate search. So even if the PCB board is not exactly in place or the insertion holes are not exactly in place, I will repeat this point. You can see how the robot searches very delicately using force feedback, and then once it's find the right position, it inserts the component in, compliant with the required quality standard. Another important aspect here that I would like to stress is the continuous flow of data and the continuous alignment of the digital twin simulation environment and the planning environment with the physical robot. Due to the fact that you have the direct connection to the robot that goes to the shop floor through the software solution. So if we look at that, we start usually from the design phase. We design the workstation, we lay it out, we insert the virtual robot, the equipment, and it's all connected to the payment backbone, to Teamcenter. Then the next step is switching to the advanced robot offline programming simulation together with the ArtiMinds plugin. In the next step, you switch to the actual robot. You perform some, you download the robot program to the robot, you perform some touch-ups, you finalize the program, and basically launch the robot into production. In all the cases, both during the touch-ups and during updates from the shop floor, it's also connected with direct connection. The updates you make are always fed back into the simulation environment, which is always consistent with the actual situation on the shop floor and subsequently updated back to the planning environment and the Teamcenter. So everything is always consistent, and in this way you avoid mistakes, you avoid discrepancies, and you always have the alignment between the planning simulation and the actual shop floor environment. So here I would like you to hear from directly from a customer that adopted this tool. The customer is BSH. And BSH is one of the biggest manufacturers of home appliances in the world, and they manufacture under many brands like Bosch, Siemens. For those located in the US, you might be familiar with the Thermador brand. So traditionally, BSH uses a single-purpose automation provided as turnkey projects by system integrators. In case of change, service or update are required, the system integrator is called. So while they keep this approach for some of their projects, they made a strategic decision to drive flexible automation in the shop floor by the shop floor engineering departments, internal departments. So they have been an early adopter of this technology and already implemented it in various manufacturing applications like screw driving, snapping, coating, testing, and others. So let's hear it directly from the customer.
My name is Frank Alexander Hanke, and I'm from Munich in southern Germany. I'm working for BSH Home Appliances. And today I would like to tell you about a project is focused on automation, especially robotics, lightweight robots, etc. So first of all, some insights into BSH. We are one of the biggest home appliance manufacturers in the world. And the chances are, I would say, quite high that you even own one of our products, as we are having several brands under our roof. So we manufacture appliances under the Siemens brand, under the Bosch brand, or even if you're in the United States of America, you might know Thermador brand, so also belongs to us. We have 42 factories altogether globally in BSH, many of them in Europe. We have aging workforce. We have to deal with productivity in high-cost countries. So one of our goals is clearly to have more automation, to really implement more robotics, be it industrial robots or newer types of lightweight robots in our assembly lines. So what we do here is we're using Process Simulate advanced robotics simulation to set up a simulation study in order to validate if a certain automation project makes sense. The new thing, though, here is that we have a cooperation also with ArtiMinds. It's a German company based in Karlsruhe. And well, it's a cooperation between Siemens and ArtiMinds now, and ArtiMinds developed a plugin for Process Simulate, which allows the engineer to take a certain operations from a library, allocate it to a robot, and the robot actually does it automatically, and the intelligence software writes the specific program for the robot in the background. So I, as a user, as an engineer, I have to select a specific type of robot, and the software then writes the specific code, and I, as an engineer, I don't have to do that anymore. So we in BSH believe that this software toolchain will help our engineers to do more with robotics on their own, because we want to foster flexible automation. Today, as many other industrial companies, I imagine, when we want to go for automation, we hire external partners and integrators, and they sell us the whole project more or less in a black box. They come to our factory, they do everything, the setup, but then later next week, we might have a product change, or we might have an optimization project on the shop floor running on. We have to call the external partner again, they have to change it, and so on and so on. So we cannot really go into flexible automation. We have a single purpose automation today in BSH. And if we want to raise the number of robots in our factories, we think we have to go for flexibility, and therefore we have to do more on our own, and we have to enable our engineers to do more on our own, and the software will help us. So to give you an example, what we did to test this tool chain, we went into one of our factories. Here it's a final assembly line for a gas cooktop. And the colleagues over there, they thought already about, okay, how to automating a screwing process. So we looked into the manual task, we set up the entire study in Process Simulate, and we did the feasibility. Is it possible? Will the robot fit into the existing line? Do we need the cycle times? Do we have an impact on productivity, positive or not? So yeah, as I said already, so why are we doing this, right? I mean, it's all about cost, productivity, time, validation in an early phase of the planning state, obviously. But we really want to empower robotics. We want to get into a position where our engineers deal with robotics more on their own. We want to go for flexible automation, like I said. And we think that those are the right tools for the engineers to come into position to be really able to do that.
So let's have a look at the applications that this solution enables you to program quickly and efficiently and achieve a robust and consistent result in each production cycle. So I would like first to look at the electronic parts assembly domain. On the left here, you see the box building scenario where you kind of build the final electronic box at the end of line of the manufacturing line, and here you can see several steps: PCB insertion, flexible keyboard made out of silicone. You will see in a second. Then there is the cover box, which is a snap fitting process. Everything, by the way, that you see here is postal control actions, and then finally insertion of the memory module. So as you can see, a full set of the final assembly operations that is performed, and on the bottom you can see the accompanying study, the simulation study in Process Simulate, including the program that was created and this the simulation of the process. Here, by the way, the programming method is a hybrid method, which means that you have both the simulation environment and the real robot, and you can program interactively and basically perform the parameterization of the template with the actual robot and play the simulation in the simulation environment. On the right, you see another application, which is a wire harness insertion into a motherboard. Again, something that is very challenging to program with the traditional programming methods, integrating postal controlled assembly or insertion of the wire into the socket. So here you can see the robot performs this robustly, and it basically can pick up the wire harness from the stand, and by searching algorithm applied here, snap it into place with the right forces and lock it down. Again, something that is very challenging to program in the standard way, and it's performed repeatedly and robustly with the robot. Again, at the bottom you see the simulation environment with the accompanying view on the robot program that was built in order to address this scenario, this use case. And by the way, all these programs were created within a few hours. So this is something that doesn't take you a long time using the intuitive programming, and creates very robust results in a very short time. Next, flexible parts assembly. So let's start from the left. On the left side, you can see flexible wire insertion into a connection terminal. So here, this is actually something that was built for Siemens rail division, and basically it's designed to replace manual operation. Something that is very labor intensive and very time consuming. So here there is a vision system that basically reads on the wire recognition the ID of the wire. It knows exactly out of that to which terminal socket it should go, and then the robot picks this up from the rotating fixture and inserts it into place using, in this case, a spike search approach. And once it's snapped into place, it also performs a pull test to ensure that it's snapped into place and is fixed in the connection socket. Again, below you see the simulation of the entire system and the accompanying program. On the right, you see actually a mechanical device assembly, a rubber hose insertion. So here you pick up the hose, and then the camera detects exactly the position of the hose, because the shape of the hose is different every time. And the camera basically identifies the position of the hose inside the gripper, adjusts the TCP on the fly so that it's aligned with the central line, and then inserts it onto the pipe extension again with a force-torque controlled motion. Next, examples, mechanical assembly. So on the left, you see an assembly of the cylinder of a reciprocal pump. And again, a sequence of few operations performed by the robot, some insertions of some pins into the gasket area, and then subsequently there is the pickup of the cover itself and the insertion of the cover on top of the pins. So again, a sequence of force-torque controlled operations in order to complete the final assembly of this mechanical device. So let's have a look at the right. In this case, it's a servo motor assembly. So here the robot picks up the servo motor from a conveyor and then puts it on the target conveyor by a spiral search algorithm to insert it into the fixture, and then picks up the spacer and inserts it also with a force control spiral search method onto the shaft. So again, a very nice mechanical assembly example, which basically show how quickly and efficiently you can build the sequence of operations required to assemble the servo motor. I would like to summarize. So what we have seen is a new approach to programming, a task-based approach without code writing, zero code writing, that allows you to easily automate even quite complex force-torque and vision control tasks, as you just saw. It's adaptive to manufacturing variances. The robot is able to compensate for deviations in the parts or in the positioning of the parts, which saves a lot of money. that you save on exact positioning of parts and equipment with tight tolerances. And of course, it's vendor agnostic and supports many major robotic brands. So you program any robot that you have in the same style, with the same approach. And this allows you to standardize your programming methods to all the robot vendors that you have on your shop floor. And with that, I would like to conclude. Thank you for the attention and goodbye.
Change.